From the ice cube clinking in your glass to the steam rising from your coffee, matter is constantly changing form all around us. But have you ever stopped to think about what's really going on at a level we can't see? Well, today we're going to do just that. We're going to go on a little journey to uncover the secret life of matter. I mean, think about it. We've all watched an ice cube melt, right? It's one of the most common things in the world. But inside that little block of ice, there's this incredible, microscopic drama unfolding as it turns into a puddle. It's a process we see every single day, but we're about to look at it in a whole new way. And you know what's wild? The answer to that question, and really to every change of state in the universe, it all boils down to one single powerful concept: energy. Yep, usually in the form of heat. Whether you're adding energy or taking it away, that's the engine that drives every single one of these amazing transformations. So when we talk about a change of state, what do we actually mean? It's simply a physical change. The key thing to remember is that it's reversible, and it doesn't change what the stuff is made of. A water molecule is still a water molecule, whether it's locked up in ice, flowing in a river, or floating as steam. It's all the same stuff, just arranged differently. Okay, to really get this, let's follow a single water molecule. We're going to go on a journey with it, starting from when it's all packed in and rigid as a solid, and see what happens as we turn up the heat. So let's meet our hero, one little H2O molecule. Right now, it's trapped. It's stuck in this rigid crystal structure we call ice. Sure, it's vibrating a little bit, but it's basically locked in place, held tight by all its neighbors. It doesn't have a lot of energy to move around. But then we add some warmth. As our ice cube starts to absorb heat energy, our little molecule starts to vibrate more and more violently. And eventually, it gets just enough energy to break free from that rigid grid and start sliding past its neighbors. And that, my friends, is melting. So our molecule is now happily swimming around in a puddle of liquid water. But what happens if we keep adding energy? Let's imagine that puddle is now in a pot on a stove. We're about to really kick things up a notch. As that water absorbs more and more heat, our molecules start zipping around faster and faster and faster. Pretty soon, it has so much energy that it completely breaks the bonds holding it to the other molecules, and it just escapes. It flies off into the air as a gas, what we call steam or water vapor. That whole process is called vaporization. And this leads us to a really important idea, the boiling point. This isn't just a gradual change. It's a very specific temperature where that frantic, energetic escape happens all at once, everywhere in the liquid. For water, as we all know, that magic number is 100 degrees Celsius, or 212 Fahrenheit. Okay, so our molecule has reached its most energetic state. It's a free-flying gas particle. But you know what they say, what goes up must come down. So now let's start taking energy away and follow that same molecule on its return trip, all the way back to being a solid. And what's so cool about this is that the return journey is the exact reverse of the trip up. If vaporization is all about gaining energy to break free, its opposite, condensation, is all about losing that energy and clumping back together. Just think about a bathroom mirror after a hot shower. All that steam in the air, that's our high-energy water molecule. When it hits the cooler surface of the mirror, it loses its energy really fast. And it's forced to bunch back up with its friends to form little droplets of water. That's condensation, happening right before your eyes. And guess what? We see the exact same mirrored pattern for the next step down. Freezing is the exact opposite of melting. Instead of gaining energy to get moving, you're losing energy to lock in place. So let's take our liquid water and pop it in the freezer. The freezer's job is to pull heat away from our molecule. It starts to slow down, it gets more and more sluggish until it just doesn't have enough energy left to slide past its neighbors. It gets locked right back into that rigid crystal structure. And just like that, it's ice again. Okay, so we've seen the standard route, right? Solid to liquid to gas and then back again. But what if I told you that matter doesn't always play by those rules? Sometimes there's a fascinating little shortcut. That's right. For some substances, under just the right conditions, they can skip that whole messy liquid phase. They can jump directly from being a solid straight into being a gas. This incredible process is called sublimation. It happens when the particles in a solid absorb enough energy to not just break free and slide around, but to completely overcome all the forces holding them together and just launch directly into the gaseous state. The most famous example, of course, is dry ice. That spooky fog you see pouring off it, that's not smoke.
That's solid carbon dioxide turning directly into CO2 gas. It completely skips being a liquid. How cool is that?
Wow, we've been on quite an adventure with our little water molecule. So now let's zoom out and look at the big picture, the one universal rule that this entire journey really teaches us. So when you put it all together, we've seen these 5 key processes. We have melting and its opposite freezing. We have vaporization and its opposite condensation. And then we have that special shortcut, sublimation. These 5 changes pretty much govern the physical world as we know it. And here's the thing, it's not just about water. This principle is universal. I'm talking everything. A block of iron, a chunk of rock, everything has a melting point and a boiling point. It's really just a question of supplying enough energy to get there. Which leaves us with a really fun final thought. If everything really can change its state, what would it take to melt the hardest natural substance on Earth? Go ahead and look it up. The answer is pretty mind-blowing. Thanks for joining me on this journey.